So, question. I sent out that announcement, was like, I don't have any, I don't know what you're doing. Someone sent me clandestine screenshots from class that they took with their phone. Does that mean she's not giving you notes anymore?
She's never given us notes.
She's never given you notes. You had these notes that were like slides or something for a while. Did she stop giving you slides?
We just started the new unit.
Totally cool. The pictures were great, but I just was curious. I was like, did things change and she stopped giving you notes? I think the pictures worked great. I looked through the pictures. The good news was, what I was planning on doing today was what the picture showed. So I was like, cool, I'm still guessing correctly, but I'm literally guessing. So if you guys want me to cover something in particular, let me know. Just you can post that to the discussion board, or you can send me an email and be like, Jen, she did this thing today and it doesn't make any sense. And I'm happy to go over it. But otherwise, I'm guessing for you. The topic today is confidence intervals.
Yes.
Question. I just handed you a scary looking table that's different than the table you've already gotten. Have you talked about the T table yet, or the students' T distribution? No. Cool. So Jen's going to be the first one to scare you with a new thing. All right. Sounds good. I put them with the confidence interval stuff because it changes up a little bit what we do. It's just going to make more sense if I explain as we go. Okay. So I'm going to jump in and explain as we go. You have this table already, the Z table. The Z table is the normal distribution. The normal distribution is like our best case scenario in the land of statistics. We're always hoping that the thing is normally distributed. But if it isn't normally distributed and we have enough things, you've got the central limit theorem that says, that's cool. It doesn't actually have to be completely normally distributed. If we've got enough in our sample size, 30 or greater, then when we take a bunch of samples, it turns out that the mean of all those samples ends up being approximately normally distributed, and so we end up getting to use the Z table anyway. But then somebody asked last week, like, yeah, but like, what if we don't hit 30? And I was like, ooh, good question. That's when we have this other table. And the other table that we are talking about is the one I just passed out to you called the students' T distribution. It's really weird. Like the word student makes you think that it's like, oh, we gave you this special one because you guys are students. It's actually got a story behind it. It came from somebody who was working in a Guinness brewery. Have you heard of Guinness beer? Yeah. Yeah, it was somebody who was working in one of the breweries who was doing samples of stuff, and he was finding out that the statistical analysis that he was doing didn't work if the sample sizes were too small. So specifically, if it was smaller than 30, it often didn't work. And so he needed this like to fudge his numbers over and over again. So he came up with this other distribution. And then other people kind of were like, oh, that's cool. That works for other stuff too. Now, he was afraid that if he published it under his real name, that then it would belong to the Guinness company. And so he decided to publish under a pseudonym. And so the fake name he picked was student. So it's called the students' T distribution. It literally has nothing to do with you guys being students. It has to do with the fake name the dude came up with for himself, which is a weird fake name to come up with. But hey, that's why it's called the students' T distribution. This is a picture of the students' T distribution. The one that she's probably going to give you probably doesn't have one tail and two tail written on it. Usually they just give you the one that just says one tail. I liked this one because it has both on there. Along the bottom, this one also is helpful when we're doing confidence intervals because it specifically breaks it down for you what kind of confidence interval to help you figure out what column you should be in. She doesn't normally give you the one that tells you that on the test. So you have to know how to use hers once she gives you hers. I don't have a copy of hers though. So I just like found one and this was the one that I liked. But once you guys get a copy of hers, we'll figure out how to like match them up. They're not that bad. It just normally yours will just have one tail along the top and that'll be it. It's not so bad. Okay. We're not going to use this yet because the problems that I picked for us to start with, use the normal distribution. But I put this chart thing on the front that she actually shared with her class, I want to say last quarter. And so fortunately, I had kept that note from somebody who had shared it with me before. So this is actually from Dr. Whitener. And it tells you when you're going to use the Z distribution and when you're going to use the T distribution. And so at the starting place, it says, hey, is the sigma known? The sigma is the population standard deviation. And if the answer is yes, then we pop over here on this side and then it says, is the population normally distributed? And if the answer is yes, we automatically use the Z distribution. If it's not normally distributed, then the next question says, okay, but is the sample size bigger than 30? And if the answer is yes, then we go ahead and use the normal distribution. And if the answer is no, we use stuff you guys haven't learned and aren't actually gonna learn in this class. So for her example, she can't give you ones that aren't gonna fall into this. Otherwise, her answer choice will be like, can't be determined or something like that. If we don't know the population standard deviation, which would mean that you have the sample standard deviation instead, then what we would do is the next thing we'll come over here and say, is the population normally distributed? If the answer is yes, we just go ahead and use the T distribution. If the population is not normally distributed, but we have a sample size that's bigger than 30, then we can go ahead and use the T distribution as well. So we'll refer back to this when we are doing our problems, but hint, I already told you on this first page, we're going to use the Z distribution because I said it's the normal distribution that we're using. So that means we're going to use the Z table. I didn't pull out my Z table yet, so I should pull out my Z table because I can tell we're going to need it. Z table. My positive and negative Z table. All right, next thing. You guys did talk about a confidence interval, but you might have been like, what is a confidence interval? We've been doing this stuff for several weeks now, where we've talked about the difference between a statistic and a parameter. The parameters are things like our symbol mu. The symbol mu is measuring what? The mean, and specifically the mean for what? For the population. Perfect. So because it's for the population, this symbol for the mean is a parameter. Population goes with parameter. It's the same letter. Okay. If I do this though, X bar, that's also the mean. But what's it for? The sample. And so if it's for a sample, that means it's a statistic. Sample and statistic go together. Population and parameter go together. Now, we ultimately always want to know things about the population, the whole population. But often it's really unreasonable for us to test the entire population. There's usually too many things in the whole population. So we take a sample instead. And we use the sample to make an estimate about what we think is true about the whole population. So what we're doing when we do confidence intervals is usually what's happening is we've taken some kind of sample and then we're saying how confident we are that the true population mean is actually within the range we just came up with. So we're using samples to try and estimate what's actually happening in the whole population. So let's think about that. I've got you guys in this room right now. And if I wanted to come up with a confidence interval to say how old I think all of you are, I'm going to say I'm 90% confident that you're between the ages of 18 and 21. Anybody younger than 18? Anybody older than 21? See, I blew it. But I was pretty confident that I got most of you in there, right? Now, so I just said that I was 90% confident. I said 90, right? That I was 90% confident that you guys are between the ages of 18 and 21. But it wasn't perfect. Okay? If I wanted to be 100% confident that I got your guys' ages right, what would be a smart number for me to start with on your age? I want to be 100% confident. But there are high school kids taking classes here. You won't usually run into them, but they're all. Youngest student we ever had graduate from here, I think, was like 10. Yeah, there's. So if I want to be 100% confident, if I put down that you are an infant, your age 0, up to, what's the oldest living person we know of?
112 right now.
112?
Yeah.
Let's put 113 just to be extra sure. If I wanted to be 100% sure.
The infant, isn't that like illegal to separate baby and child before like?
Well, because I'm saying years if they're not quite, so maybe we got it.
Are we counting like grad students that are like pregnant and are like coming to class?
Sure. Then extra sure, right? If I wanted to be 100% confident I got all your guys' age, I had to make that interval wider. This is a pretty narrow interval. It only goes from 18 to 21. It covers 3 numbers, right? This one covers 113 numbers. If I make it wider, I'm more sure that I've got all of you in there. So when you do confidence intervals, when it tells you to do like a 90% confidence interval versus a 95% confidence interval, if it's a 95% confidence interval, then we got to widen this out and maybe we'd say 16 to 24, right? And if we wanted to be like a 99% confidence interval, we might say like 14 to 40 or something like that. And so we make it wider if we want to be more confident. But if I don't need to be as sure, then I can narrow it down and I can pick numbers that are closer together. Now, this, if I wanted to say an estimate of people in this room, and I said, yeah, I'm pretty sure you guys are between the ages of 0 and 113. How good of a job have I done of giving the average age of college students in my class? A crappy job, right? So when you want to be 100% sure, what you have to give up is usefulness of your measurement. So what we do is we kind of do this balance and we go, well, I'm going to risk the chance that I guess somebody's age wrong, like I did in this case, and I did that on purpose. I was pretty sure that I almost always have people who are outside that range. I risk the chance of being slightly wrong in order to give you a pretty good estimate of how old people are on average in the class. Or I give you a very useless number, but I can be completely confident that you're in there. And so we have to weigh that out. Okay. So let's look at an example. Among various ethnic groups, the standard deviation of heights is known to be 3 inches. So they're saying if we had a room full of people who are ethnically Japanese, and then we were divided, we have to divide between males and females usually, because typically males tend to be taller than females. So if we choose just males who are ethnically Japanese, even though their heights are different than people who are ethnically Swedish, in that range, they're saying the standard deviation for those various populations is still 3 inches, so that all Japanese men have a standard deviation in their heights of 3 inches. And if we stick with another ethnic group, then that actually tends to be true. I don't know if this is true. This came from your statistics textbook. So I'm going off what it says. It could totally be a lie. But it's saying, among various ethnic groups, the standard deviation of heights is known to be 3 inches. We wish to construct a 95% confidence interval for the mean height of male Swedes. So Swedes are males from Sweden. 48 male Swedes are randomly surveyed. The sample mean height is 71 inches and the sample standard deviation is 2.8 inches. Okay, they gave us a bunch of stuff there. The first question says, list the statistics and parameters that are given to you in the problem. Okay, so first thing I see in here is it's saying that the standard deviation of heights is 3 inches, and it's just saying all heights. So that one's a parameter. And the top one is a mean and the bottom one is a standard deviation, right? If I want the mean for a sample, that's going to be this symbol. And if I want the standard deviation for a sample, that's going to be just in lowercase s. Okay, we're going to see what we got. We might not have gotten all of these things. Okay, standard deviation of all heights. That's population. Known to be 3 inches. So that's going to be this symbol right here. Because that's all of them. All right. 48 male Swedes are randomly surveyed. The sample mean height is 71 inches. So sample mean is this one, the X bar. And the sample standard deviation is 2.8 inches. So I got this one. What I did not get is the population mean. What they want us to do when they say, we wish to construct a 95% confidence interval for the mean height of male Swedes, they're saying they want us to find the population mean for them. So we don't have this one. I'm going to put a question mark there. This is the one that we're going to estimate by finding a confidence interval. Okay. Find the 95% confidence interval and interpret the result. All right, you guys got a formula for a confidence interval that had some crazy looking symbols in it. Specifically, I believe, since I have last year's formula sheet, I believe you got a formula that looks like this. You got an X bar, which is the sample mean, plus or minus a Z with an alpha divided by 2 times, and then we got the sigma symbol, so that's the population standard deviation divided by the square root of the sample size. And then I believe she probably spent a lot of time talking with you yesterday about that Z alpha over 2 part, because it's a little scary looking and we have to kind of understand what that is. So I'm going to go ahead and copy that formula here so that I have it to look at. X bar plus or minus the Z sub alpha over 2 times sigma divided by the square root of our sample size n. That's going to help us come up with a confidence interval. All right, we have some of these numbers already. One of the numbers that I haven't written down yet when we were writing the statistics and the parameters up here, I didn't write down what the n is for this problem. What was our sample size? Yeah, 48. Cool. So in the formula, the X bar, we already have that. That's a 71. We've got the sigma, that's a 3. We've got the square root of n, that'd be the square root of 48 then. Notice I actually don't need the sample standard deviation for this problem, because the formula doesn't use the sample standard deviation, it uses the population standard deviation. I very specifically wanted you to write all those things out so that you can see that sometimes they give you numbers you're not going to use. We're not going to use that S in this problem. If you use the S in this problem, you're going to get it wrong. And so that can mess with you on homework problems too, if they give you like more info than you need. So when we do these, and we're actually talking about the normal distribution, we need the population standard deviation. I don't want this one. Okay. Now, this Z, I don't have that. Z alpha over 2. What did she tell you the alpha means?
You take the confidence, like, you take the confidence interval that you're looking for, and then
Yep.
whatever's left is the alpha.
Cool. So we asked for a 95% confidence interval. So if it's a 95% confidence interval, I'm going to write 95% CI. I'm going to be lazy. That stands for confidence interval. My alpha is going to be, as a decimal, 1 minus that percent. So when we're doing a confidence interval, we want a 95% confidence interval, then that means that the alpha over here is going to be the decimal equivalent of 5%, because 100% minus this 95% would mean there's 5% left over. Okay. And so she probably drew you a bunch of pictures, is my guess. When you have a 95% confidence interval, then the 95% is in the middle part. And that means that you have 5% left over. And so that means that over in this tail over here, that's going to be 2.5%. And then in this tail over here, that's going to be another 2.5%, because together that's going to make up the 5% that's going to add up to the whole 100%. So if we do 2.5% plus another 2.5%, that's 5%, plus 95% would be the full 100%. Is that okay? So when we're doing a confidence interval, what we need to do is figure out what's in each tail. So whatever number you get, you divide it by 2. That's why it's alpha over 2. So it's 5% total, but we need to figure out what's in each tail. So we divide by 2 to figure that part out. Okay. Now, this Z, alpha over 2, I want to find the Z. And so when we looked at our Z tables, on a Z table, the Z's are along the edges and the percents or the probabilities are in the middle of the table. So what they're asking us to plug in here, they want the Z. In order for us to get the Z, we got to figure out what probability or percent we're talking about. Okay. And we have 2 choices. She probably talked about how by definition, Z alpha over 2 is always a positive number, but really we can use the negative number to go figure it out, because what we'll do is we'll just make it positive. So if there's 2.5% in this tail, as a decimal, 2.5% is 0.025, because we moved that decimal point over 2 places to turn it back into a percent. So if this is 0.025, then that means over on the other side, if I wanted to know what that is as a decimal, I don't want it to be 0.025 to figure out where that mark is. So this 0.025 is where that bar is right there. So I would do 1 minus 0.025 to figure out what this bar is right here. That's 0.975. Didn't put my point very good. There we go. 97.5% is what that would be if you move the decimal point over 2 places. 97.5. 97.5 plus 2.5 more gives you 100%. It actually doesn't matter which of these 2 numbers you use. Both of them will give you the number that you need from the table. So I usually, when we're doing this and I figure out that there's 2.5% left, I just go ahead and move the decimal point over, and then I go find that number on the table. But the number I'm going to get is going to be a negative number. Doesn't matter. I just need to make it positive when I use it in the formula. If that bothers you though, and you're like, I'm gonna forget that, then what you wanna do is you wanna figure out what this number is over on this side. This one's gonna give me the positive version of that same number. I'll show you what I mean, so that you can be like, oh, that's what you mean, Jen. Okay. So first thing I'm gonna go find is 0.025 on my Z table. That's gonna be on the negative side of the page because that's where all the tiny numbers are. 0.025. 0.025 is right here. So if I come across 0.025 is negative 1.96. Negative 1.96 is the Z value for right there. So I'll write that in a different color. So the Z value for 0.025, negative 1.96. So that matches up with this number right here. Okay. If I go look for 0.975, then I'm on my positive Z table. So I'm going to go find 0.975. 0.975 is right here. If I come across, I get positive 1.96. Positive 1.96. So what I mean is you actually don't need to figure out both of these numbers. If you can just figure out that this one is 0.025, you're going to get the number you need. It's just going to be negative. You just got to take the negative off. 1.96. 1.96 is just that one had a negative on it, but when we use the formula, we don't make it negative. Is that okay? So we're going to use Z alpha over 2 is equal to 1.96 in this formula. Our alpha for this problem was 0.05. I forgot to fill that in before. Okay. We have everything we need to plug in. So my X bar, we said was 71. Plus or minus. Now we're plugging in the Z alpha over 2, which is 1.96. Then we're going to plug in the sigma. We said that was 3. And then we're going to put the square root of n, so square root of 48. And now it becomes a calculator problem. So I'm going to do this part first. That's called the error bound measure. Did she talk about the error bounds? Maybe, kind of, sort of. Right here is your error. So I'm going to do 3 divided by the square root of 48. And then I'm going to multiply that by 1.96. Okay, so what I got was 71 plus or minus 0.84. I'll say 87. I'll put a few additional decimal points down, and then at the end, I'll round it to 2 decimal places, maybe. Okay. The plus or minus sign just means that one of the times we have to add that number, and one of the times we're going to subtract that number. So we're going to do 71 plus 0.8487. That'll give us the bigger number. And then we'll do 71 minus 0.8487. That's going to give us the smaller number. So when we write our confidence interval, we put the smaller number first,
and then the bigger number second. So doesn't matter. You could decide to do the subtraction first if you want. Let's do the subtraction first. 71 minus 0.8487. If I round that to 2 decimal places, I get 70.15. That's my smaller number. And then I'm going to do 71 plus 0.8487. And if I round that to 2 decimal places, I get 71.85. Right, we have a confidence interval. But what does that mean? Okay. So I have up here, find the 95% confidence interval and interpret the result. All right. We are 95% confident is how we're going to start this because it's a 95% confidence interval. So I'm going to say we are 95% confident that. What was I trying to figure out? What was the thing I put a question mark after?
The height of male seed.
And this is the true mean because it's for the population. This was just the sample mean. We were trying to find the true mean. So when we're talking about the population, we often use the word true to say the actual population mean. So I'm going to say we are 95% confident that the true population mean height of male Swedes SWEDES is between 70.15 inches and 71.85 inches. That's what it means when it says interpret. So you'll end up with an answer that's just numbers in there, and then you need to turn the numbers back into that actual problem situation. So 70.15, 71.85, what does that actually mean in terms of this problem? We're saying that we don't know for certain, but we're 95% confident that the true mean height of male Swedes is between 70.15 and 71.85 inches. That's a pretty close estimate. That's not like us saying between 0 and 113 years of age. That's much more like, oh, between 18 and 21 years of age. It's a much more narrow confidence interval. So the next part of the question says, what will happen to the confidence interval if 1,000 male Swedes are surveyed instead of 48? Now, I don't want you to even do the math on this yet. If I only ask 48 people their heights, or I go spend hours longer and I ask 1,000 of them their height, do you think I'm going to get a more accurate estimate, or I'm going to have to make it a wider estimate like we did over here? You spent more time. You spent lots more time to ask 1,000. Is it going to get narrower or is it going to get wider? Remember, narrower is good. Wider tells you nothing. Narrower. If you ask more people, it's going to get narrower. And that's just reasonably speaking. if you go ask more people, then you should get a better estimate, right? A better estimate for the age of people in here is that you're between 18 and 21 than it is to say you're between 0 and 113. Like, obviously, you're between 0 and 113. This is a better estimate, right? So if I only ask 48 people, I'm gonna get an okay estimate, but if I ask 1,000 people, I should get a better estimate, right? Because I'm asking more of them, so I should get rid of more of the variation of a better estimate if I ask more. Intuitively, it makes sense, but mathematically, it makes sense for a reason that has to do with the formula in here. That's where that number is gonna go. And so, if I put a bigger number down there, let's think of a number that you're good at dividing out. Okay, if I do 100 divided by 20, or I do 100 divided by a bigger number, 50. What's 100 divided by 20? 5. If you're scared by that, you can actually wipe out the zeros here that are in common. So you can say, what's 10 divided by 2? That's 5. So 5 pops out. When I divide this by a bigger number, because 50 is bigger than 20, dividing by a bigger number, what pops out when I do 100 divided by 50? 2. If I divide by a bigger number, I get a smaller number to pop out. So up here, if I divide by a bigger number like 1,000, then this number is going to become smaller overall. And if that number becomes smaller, that means your error bound becomes smaller. So you're going to be doing 71 plus or minus a smaller number. And if it's 71 plus or minus a smaller number than we did before, then it's going to be a narrower confidence interval. So we're going to say the confidence interval will get narrower. Mm-hmm. So I wrote, the confidence interval will get narrower because dividing by the square root of 1,000 will make the error bound measure decrease. And you wouldn't have to use those exact words in order to get this correct. You could say lots of different things. You could say if you're dividing by a bigger number, it's going to make it a smaller number overall that you're adding to your sample mean.
If this was on like a exam or some kind of assignment, would they want it written out in words, this kind of answer, or would they want to prove that?
She will sometimes actually say prove mathematically, and if she doesn't, then writing out the words is fine. Yeah. You'll have some homework questions that are multiple choice that will ask you what will happen when you change certain parts in this formula. So in the formula up here, there's other things we could change. If we make the sample size bigger, then that means that we get a narrower confidence interval. If we make the standard deviation bigger, what do you think happens? Yeah, it makes it a wider one because standard deviation means there's more variation in the numbers. So that means you're going to have not as good of an estimate anymore. So if the standard deviation gets bigger, we have a wider confidence interval. If the sample size gets bigger, we have a narrower confidence interval. If we change the z, that means we change the confidence interval. So if I change the confidence interval to be less confident, so if I say 90% confident instead of 95% confident, am I narrower or am I wider? And remember, when we made it 100% confident, it was hell's a lie. So if I go from 95% confident to 90% confident, it should get narrower. If I go from 90% confident to 100% confident, then I had to make it hell wide.
If we say like smaller instead of narrower, will that still be correct?
Smaller should be fine, yeah.
Okay.
Good question. I know words sometimes you're like, is that okay? Smaller should be okay. All right, let's look at another one. A sample of 16 small bags of the same brand of candies was selected. Assume that the population distribution of bag weights is normal. The weight of each bag was then recorded. The mean weight was 2 ounces with a standard deviation of 0.12 ounces. The population standard deviation is known to be 0.1 ounce. Okay. Lots of words there again. First thing I want to point out, our sample size in the last problem was 48. So you probably didn't have any moment in time when you were going, are we on the right distribution? This says 16 though, and 16 is not 30 or bigger. So you might have a moment where you go, I don't know. Am I allowed to go use the Z distribution? So this is where for chart is handy. It says start. Is the sigma known? Oh, sorry. Start. Is the sigma known? And that's what tells us, do we go this way or do we go this way? Did we get the sigma in all those words? We did. The very last line says the population standard deviation. That's the sigma. So I'm going to write down mu sigma X bar and S again. And we'll see what we got. Sigma we have is 0.1. Off to the side, our N is 16. I can write that down as well. Okay. The weight of each bag was then recorded. The mean weight was 2 ounces. So they took 16 small bags and then they found the mean weight. That's the sample mean. So this is 2. And the standard deviation for that sample was 0.12. So again, the thing we don't have is the population mean. Question.
It says that you assume that it's normal. Doesn't that mean it's the same thing, the X bar and the mean? Or no?
So all this is talking about is the distribution of where the things are coming from. And so when we're talking about the distribution of where they're coming from, we're still going to be trying to figure out what's true of the entire population based on the tiny sample we're using. So this part, the X bar, is always referring to, are we talking about a sample or are we talking about the whole population? So X bar, that's going to be sample mean. Whether or not this is normal or not, this has to do with this chart. Okay, so let's say we had not had the sigma here. We did have the sigma, so we're going this way, but let's pretend we didn't. We didn't have this, we'd go this way, and then the next question is the population normally distributed? They just told us it was, so we get to go this way. Okay, over here, is the sigma known? Yes, it was. We got the sigma. So now we came over this way. Then it says, is the population normally distributed? Yes, it is. So we're going this way. We automatically use our Z table then. Okay. Often, in the real world, you don't know what distribution. So, also often, we don't know the population standard deviation. That's like, if you know that, you know a lot about where this number is coming from. We almost never know this. So truthfully, like as someone who's done statistics for studies and different things like that, I never got to use the Z table. Wasn't a thing. Most statisticians are living over here on that T table. And actually in the real world, you're not using a table, you're plugging it in to a statistical analysis software package. But this is like very rare to actually get to use these, but it's what we start with because you guys learn how to use that table first. So they give you problems that are very not real first. And then T is way more real. Yeah. Okay. So again, we don't know what the population mean is. That's the thing we're going to estimate with our confidence interval. So let's see what they want from us next. Construct a 90% confidence interval for the population mean weight of the candies and interpret the result. Okay. So the formula that we're going to use is the same formula we used last time. So I'm going to write it down again. X bar plus or minus the Z sub alpha over 2 times the sigma divided by the square root of the sample size n. Okay. We've got the X bar, that's 2. We've got the sigma, that's 0.1. We've got the square root of n, that's going to be the square root of 16. They again gave us a number we're not going to use. We're not going to use the sample standard deviation because when we use this from this chart, what we needed was the sigma. We got that. Okay. So the number we don't have is the Z alpha over 2. We're not going to use 1.96 like we did on the last problem because that was for a 95% confidence interval. This one, we want a 90% confidence interval. So if it's a 90% confidence interval, what's our alpha? Right, 0.10. So 90% means 10% is what the alpha is, and we write it as its decimal form. So that means that each tail of your distribution then, if this is the 90% in the middle, if the rest of it makes up 10%, then you have 5% over here. And you have 5% over here. But we don't use 5%, we turn it into its decimal form. So we're going to be going to look for 0.05. Or you're going to be looking for 0.95. Either one. If you look for the 0.05, you're going to get a negative number for the Z. If you look for the 0.95, you're going to get a positive number for the Z, but the number itself is going to be the same number. If you took the absolute value of it, it's the same number. So you don't have to write down both of these. I usually just write down that one and then I remember that, oh, I'm going to get a negative number, but I'm going to make it positive. So my Z alpha over 2, let's go get from our chart. So 0.05. Okay. 0.05 is not a perfect number here. We have 0.0505 and we have 0.0495. So this would be one of those scenarios where she said, go with the closer one. There isn't a closer one. They're both equally close. So I would go with the number right in the middle, which the table is also giving us a cute little star there to say this is a very popular number that pops up a whole bunch. So the number that pops up a whole bunch, I'm not going to write down negative 1.6. I'm just going to write down positive 1.6. And then in between here, we got a 4 and a 5. So we're going to write 4, 5. So it's positive 1.645. Positive 1.645. Yes. So whenever we do these ones, I can either, if I do this one, I'm going to see the negative sign, but we could have also used the 0.95. The 0.95, we're going to have the same thing, but it's going to be positive 1.645 when we go to do it. doesn't really matter if you get it from the 0.05 or the 0.95, but the problem is whenever we do the Z alpha over 2, Z alpha over 2 is always going to be a positive number. Always, always, always. So you can do it either way you want. But if you use the smaller one and you get the negative number, just drop the negative sign. Yeah. Cool. All right. Now we're ready to plug our stuff in. Our X bar. Oh, sorry. I just moved it. My X bar was 2. Plus or minus, my Z alpha over 2 is 1.645. My sigma is 0.1, and I'm dividing it by the square root of 16. When I multiply these two numbers together here, that's going to be my error bound measure. Point 0.1 divided by the square root of 16 is just 4 times 1.645 means my error bound measure is 0.0411 if I write a few extra decimals. And so again, with that plus or minus sign, that means you're going to one time take 2 plus that number and one time do 2 minus that number. So you're going to have the smaller number over on the left and the bigger number over on the right. So I'll do 2 minus 0.0411 first. And that gives me 1.96 if I round it. And then 2 plus 0.0411 gives me 2.04 if I round it. So the question was, what is the mean weight of the population for those candies? So all of the candies in there. So we're going to say I am, or we are 90% confident that the true mean weight of each bag is between 1.96 ounces and 2.04 ounces. So, oh, question.
Will we ever be asked to actually like find from you for this kind of problem? Like I know you found like what it's between the three, that's like. What it is.
Are you saying the true population mean? You can't.
Okay.
Impossible. So we're just coming up with our best possible estimate that we could, but then we're choosing for ourselves how confident we want to be. So we got a pretty darn good estimate. We're 90% confident it's between 1.96 and 2.04. But maybe you are part of a research team and they say that's not good enough to be 90% confident. They want you to be 98% confident. Okay?
The only thing that's gonna change in the problem, if we want it to be a 98% confidence interval instead, is that Z alpha over 2. Everything else we do is gonna be exactly the same. So if we're gonna construct a 98% confidence interval, I need the new Z alpha over 2. So for a 98% confidence interval, my alpha then is 2%. So that's going to be 0.02. Which means that %98 is in the middle, which means that there's 1% over in this tail. And there's 1% over in this tail. So if there's 1%, that would be 0.01 as the number there. Or you could go look for 0.99 if you wanted. If you find 0.01, you're going to get a negative Z, but you're just going to make it positive. If you find 0.99, you'll get a positive Z. So 0.01, if I do that, is going to be between negative 0.102 and 0.0099. So that one would actually be closer to this one ever so slightly. So that would be, I won't put the negative sign on it. We'll just put positive 2.33. Positive 2.33 if we're going with the closer number. We could have also looked for 0.99. If we do that instead, 0.99 would be right between these ones. So it would be a positive 2.33. So either one will get you the number. It's just if you do the smaller one, it's going to be negative on the table and you just have to remember to make it positive. Okay, so our formula is still going to be the X bar plus or minus that Z alpha over 2 times the sigma over the square root of n. So we're plugging in the same X bar, which was 2, plus or minus, now we're going to use 2.33. And then everything else is going to be the same. So our sigma is still going to be 0.1 and square root of 16. So 2 plus or minus, I'll get my error bound measure. Oh, you okay? Ouch. 0.1 divided by square root of 16 is 4. Times 2.33. It's going to give us 0.058. So I'm going to do 2 minus 0.058. And that'll give me 1.94 if I round it. And then 2 plus 0.058 will give me 2.06 if I round it. So just like we talked about with ages in here, the 90% confidence interval was narrower than the 100% confidence interval, which got wider. The 90% confidence interval for this one was 1.96 to 2.04. The 98% confidence interval got wider. It's 1.94 out to 2.06. So in order for it to be a bigger confidence interval, we had to make it wider. Right. I don't know if you've seen this formula yet. She might not have given you this one yet to find the sample size that you need. But here it is. She will give it to you. It's on the formula sheet for midterm 3. The average height of young adult males has a normal distribution with standard deviation of 2.5 inches. You want to estimate the mean height of students at UC Davis to within 1 inch with a 93% confidence. How many male students must you measure? So this one is not asking us to find the confidence interval. It's telling us we want to be 93% confident. So what would be the sample size that we need? The formula says we want the sample size. We got to go find the z-score that corresponds to the 93% confidence interval. We got to find the population standard deviation. And we need the error bound measure. The error bound measure in this problem is always when they say, we want you to estimate it within, and in this case it says 1 inch. Our error bound measure on this one is 1. So if they say they want you to go find it to, plus or minus 3, then the error bound measure would be 3. If they're telling you they want it to be within 1 inch, that means plus 1 inch or minus 1 inch is okay. So they gave us some information here. They said the average height of all of the adult males has a standard deviation. So our sigma for this problem is 2.5. Okay. Our error bound measure we said is 1. And so the thing that we need is the z. Okay, so the z that we would get for a 93% confidence interval means that we have an alpha of what? Seven. Yes. So if it's a 93% confidence interval, then the alpha is 0.07 because the 93% means that there's 7% left over, and we turn that into a decimal. 7% as a decimal is 0.07. Okay. So now that means that you're going to have 3.5% in each tail. So the 93% is in the middle. And we have 3.5% in each tail. .5% as a decimal is 0.035. So that would be the one that I would go look up on the table, but if you wanted to do the bigger one, we have to do 1 minus 0.035, which would be 0.965. Either of them will work to get you the z. I usually just do the smaller one. So 0.035 0.035 is going to be closest to this one. So we would say, I'll leave off the negative sign, 1.81. 1.81. All right. So we're ready to plug it into our formula for n. N is equal to the z, which is 1.81 squared, times the sigma, which is 2.5 squared, divided by the error bound measure, which is 1 squared. And that comes out to be 20.48. That's not the answer we're gonna write if this was a homework question, and she'll have a homework question like this. Whenever we're trying to figure out how many male students must you measure, we can't have a fraction of a student. So we got 20.48. We always have to round up to the next whole student. So 20 isn't enough. We have to go to the next student. So even though normally if you were going to round like traditional rounding, you would be rounding this one down because it's not 0.5. In this case, you're always rounding up to the next whole number because you can't, 20 students isn't going to be enough. So we got to do 21 students. So our N is going to be 21. You want me to stop since you haven't talked about the T stuff yet, or do you want me to keep going? We got 13 more minutes. Doesn't hurt my feelings either way. You guys feel burned out? You look burned out. Let's stop. Well, let's give you 13 minutes of your life back. Good job. I know that was a lot of math there.